We're going to continue with thermochemistry. This time we're going to be talking about, it's supposed to be enthalpy, sorry. I need to fix that. Enthalpy change, enthalpy of combustion. This is the first time we are going to really apply what we learned in the first video, but like I said, the story is not going to be complete. You have to take college chemistry 2 to apply to determining spontaneity of a chemical reaction. But this is a much better chapter than what we saw in the first video, promise you. To describe the thermodynamics, the changes in energy and heat and all of that in chemistry, chemists use a property called enthalpy. Okay? This is, by definition, the sum of the internal energy plus the product of the pressure and the volume. And you say, what is that? Well, don't worry about it. This is just a definition. Okay? And the reason I tell you don't worry is because you cannot measure enthalpy directly. The only thing you can measure is change in enthalpy. Okay? But you do have the definition of enthalpy. It is a state function because, again, it does not depend on how you get there. It depends on the state you are. This is going to be important when we try to calculate enthalpy changes. Okay? But keep in mind the really important, useful term is enthalpy change. Enthalpy is represented with an H, delta H, obviously is the change in enthalpy. Why do we use enthalpy? Because, well, if you go back in here, you can see that energy changes, but pressure volume in a regular chemical reaction, the change in pressure is zero because you're working in a test tube. It's open, so the pressure is the atmospheric pressure. When a chemical reaction takes place, the atmospheric pressure does not change. So pressure volume in a chemical reaction equals zero because there's no change in pressure. That makes enthalpy a very handy number to deal with because the enthalpy change is the heat of the reaction, where it's absorbed or released, something like that, at constant pressure, which is exactly the conditions in which we're working in a chemistry lab. Okay? So, like I say, any work done by partial contraction and like that, we're not going to worry about pressure volume work until chemistry 2. It just, what I'm trying to say is that because we're working with open containers, because the pressure does not change, enthalpy is the most convenient choice for determining heat. When we write a chemical equation, but we're studying thermochemistry, you need to include the changes in energy too, changes in heat in there. So you write an equation, a balance equation, but you also add delta H. And when it's a negative number, it tells you that it's an exothermic reaction. It lost energy. If this number was positive, it's an endothermic reaction because it gained. And most students figure like, oh, something has to memorize, right? And I'm going to get confused. No, think on energy as your checking account. You go around and you're going to get something to eat and you scan your card, right? And then you get a drink. And then maybe you go by Starbucks and get a coffee. And you keep scanning your card. What happens? You're using money from your account. Your balance decreases. When you're taking money out of your checking account, you have a negative number because it's decreasing. Now it's payday and your paycheck is automatically deposited. When you're adding, it's positive because your balance increases. So if you think on energy as your checking account, then it's very easy to see that when you're losing, when you're throwing heat out, it's like losing money, you're going to have a delta H as negative. When you're gaining heat, just like when you're gaining money, delta H is going to be positive. It's a silly little thing, but it's easier than memorizing, okay? Now, there's a number of things that is going to seem like common sense, but people tend to say, oh, yeah, don't pay no attention to that. And then we're going to use them, and they don't remember a thing I said before. So all of these things are important. And I'm going to mark the things that you need to know. When you change the direction of a chemical equation, the sign of delta H is reversed. This is going to become very important if you wait long enough, okay? So hydrogen and oxygen can react to produce water, and that releases heat. But if you break down water into hydrogen and oxygen, you have to add heat. Okay? Actually, we add the energy in the form of electricity. We talk about that. It's again college chemistry 2, electrolysis. But we change the reactants become products, the products become reactants, and now it's the same number. We just change the sign from negative to positive. This is going to be important later on, okay? Promise. What if you need to change the coefficients? For whatever the reason, you're going to multiply times a number. You're going to multiply the enthalpy change by the same number. Because delta H remembers an extensive property. So if you have 1 mole of hydrogen and half a mole of oxygen, you release this energy. But you say, hey, I don't like this equation. I don't like having, we said that this number should be whole numbers. So multiply everything times 2. So I have 1 oxygen, but now because you double the amount of the reaction, you double the energy. And if you want to multiply times any other factor, you multiply delta H by whatever factor. You're going to have to do it sometimes, and you just need to remember to multiply the energy. Again, we're going to be using this a lot, okay? So this is not just a casual comment. And you need to be careful because delta H is going to depend on the physical state of the reactants. Most of the time, that's not all that important because oxygen in any chemical reaction is going to be gas, hydrogen is going to be gas, but what we said before, it can be gas or liquid. It's very difficult to form ice, okay? But this is going to happen over and over. Some reactions are going to produce liquid water, some are going to produce steam, and notice that the delta H is different. So once again, look at the question carefully. Liquid, gas, because very likely you're going to get a table that will have both values. And it's a case of putting the correct number for the particular question that you have. The question will tell you if you have liquid or gas. You just have to read the correct value for that, okay? So you have an example, and this is going to be a little bit long, but you have a gummy bear that has this amount of sugar, this table sugar, sucrose, and you can oxidize it with potassium chlorate. That's a combustion there, they give you grams in there, and this is how much heat is produced. Okay? So they want you to write a thermochemical equation. To begin with, you write the regular equation, the chemical equation. So you balance it, this is your chemical equation, but we say thermochemical equation needs to have here delta H equals whatever number. And that's what we're going to calculate. First problem, they're giving us grams for sucrose, grams for potassium chloride. So you have no idea which number you need to use to calculate. You need to know who is the limiting reactant. Because the limiting reactant is going to be used up, and that's what going to tell us how many moles you need to produce that amount of energy. You could do it 2 different ways. You can do it the way we did it when we talk about the limiting reactant, meaning change the grams to moles. If all of these moles of sucrose reacted, how many moles of, I don't know, carbon dioxide produces? If all of these grams of potassium chloride, we change into moles, they all react, and see which one produces the least. This book decides to use a different system. You can do it any way you want to, but basically they convert it to moles like we always do, and they look at the ratio of moles. And they say the potassium chloride to sucrose is 7.52. But if you go back to the equation, you need 8. 1 mole of sucrose needs 8 moles of potassium chlorate, but what they give us is 7.52. So that tells you right there the potassium chlorate is the limiting reactant. Just another way of doing it. You can do it any way you prefer. This is simpler. On the other hand, you learn to do it the other way. So whichever works best for you, that's what you want to do. But you determine who's the limiting reactant because the heat has been produced. Remember, enthalpy is the heat per mole. So this is the heat that's been produced, negative because it's been released. You divide by the number of moles, and that gives me how many kilojoules per mole of potassium chlorate. And you say, yeah, but in the original equation, there wasn't 1 mole of potassium chloride, there was 8. Okay, so you need to multiply times 8. That amount of potassium chlorate can release 5,960 kilojoules. So now you write the equation, delta H equals 5,960 kilojoules. The heat is released, so it's negative. Notice that in the calculations, well, we could have put the negative sign in there. And of course, if this is negative, but as long as you remember at the end the heat has been released, it will work. So we figure who is the limiting reactant. This is the heat that has been produced. So how much heat you produce per mole. Now the equation uses 8 moles. So you figure how much heat the full equation will produce, and you just add it to the equation. That's how you write a thermochemical equation. Really go slowly, but it's, when you think about it, common sense in there. One way to make sure that you don't forget steps, like people say, oh, I forgot to multiply times 8. I forgot. If you keep up with the units, you have kilojoules. When you divide by mole, you have kilojoules per mole. But you're going to have to be in kilojoules. Oh, that's because I have to multiply times moles. When I multiply times moles, the moles and moles cancels out and I get kilojoules. So either because you understand the process real good or because you keep up with the units, if you keep up with the units, you won't forget to divide by the number of moles or multiply times the number of moles. The units, you want to end up with kilojoules, so that takes care of it. There's 2 different ways you can make sure you didn't skip and step in there. And we do have tables of enthalpy changes for just about anything that you can never use in chemistry. Now, we are also going to have a standard state, kind of similar to when we talk about standard temperature and pressure for gases, reference temperatures, concentrations, and all of that, so that everybody's doing the reaction in the same conditions. Now, there's a problem here. This is going to be different from what we saw for gases. The pressure is going to be 1 atmosphere, is close enough, okay? The UPAC say 1 bar, but 1 atmosphere is so close that we can call it. But the solution, if you have, is 1 molar. Of course, with gases, we didn't talk about solutions. And the UPAC did not set a temperature. Okay? So what most people do is work at 298 or 25 degrees. And you say, wait a moment, with gases we were using 0 degrees Celsius. Yeah? And people have argued back and forth, why don't we just have one standard that works for gases and for regular reactions? Because the people working in those fields don't want to. The UPAC wanted to unify everything. And the people working with gases say, we don't want to work at 25 degrees because we've been working since the 1800s at 0 degrees and we have to redo all of that work. No, we're not changing. Okay? The people doing usual chemical reactions say, we don't want to be in a lab at 0 degrees. That's freezing. We work at room temperature. So they have never agreed. It all boils down to you as a student need to remember that the temperature, the standard temperature for a gas is 0 degrees Celsius. For a chemical reaction is 25 degrees Celsius. Unfortunately, like I said, UPAC was not able to get them to agree on anything, so But enthalpy at these conditions is called the standard enthalpy, and we represent that with a little zero in there. So we're going to be looking at enthalpy changes for many types of reactions. Remembers an extensive property, so many times it's more convenient, we normalize it when we divide by the amount of substance, so you have joules or kilojoules per mole. This is not a requirement, but it's going to be very, very common. How do you know? Read the questions. They will give you values, probably grams, they will give you, or you calculate joules, but in the question, they will ask you, do they want in joules or they want in joules per mole or something like that. All of that information is always going to be given in the question. Be very careful, read the question. Remember, underline anything that's important, because if you read the questions carefully, you won't have any problem with these enthalpy problems if you read the questions carefully. Okay? So we're going to begin with enthalpy of combustion. How much heat is released when you burn 1 mole of substance under standard conditions. Okay? Some people call it heat of combustion. So they say, for instance, ethanol. The enthalpy of combustion is negative because it's lost, and they give it to you in kilojoules per mole. That means that then you can calculate the heat for different amounts. This is how much heat is released when 1 mole of ethanol undergoes combustion. Okay? It releases that much heat. But then you can change the amount, and you say, okay, if 1 mole produces this much heat, 2 moles will produce twice as much, half a mole will produce only half. That's where looking at the units will give you a good idea what's going on. So here you have an example of a table where they give you, notice all of the energies of combustion are going to be negative because combustion means you're releasing heat. But other than that, there's no particular problems because you don't have to worry about state of matter here. So one example. You know, burning gas is very exothermic. You've seen a gas fire, you know what I'm talking about. So how much heat does it produce to burn 1 liter of gasoline? Okay? Well, we are going to have to make a few assumptions. Gasoline is a mixture of compounds, but the main one is isooctane. It's the most common component. So we are going to say that the heat of combustion of isooctane is the heat of combustion of gasoline, because it's the major ingredient. Okay? And you can look at the density of isooctane. Why? Because you are going to have liters of gas, you have to change it to grams, then you have to change it to moles. You know from the table how many kilojoules are going to be released per mole. So once you know how many moles you have, you can see how many kilojoules have been released. So here you have the liters of, we are just going to call it isooctane. You have to change it to milliliters. Why? Because the density is in grams per milliliter. Okay, grams per milliliter. So you have to change your liter to milliliters. Now liters and liters cancels out. So we have milliliters of isooctane. Using the density, we can change it to grams. Milliliters and milliliters cancels out. This was given to you. Okay. Now you look up what is the molar mass, because you're trying to change it to moles. So 1 mole weighs this many grams, grams cancels out. And now, if you look up in the table, 1 mole releases 5,460 kilojoules, moles and moles cancels out, and it gives you this number. The units are correct. First, because you cancel all the units, so you know, it gives you kilojoules. Second, we are looking at heat, so it makes sense. It's kilojoules. It's negative. Why? Because heat is being released, lost in there. And the only thing you need to worry about is significant figures. And this is, all of these are numbers by definition. The only number that is experimental is the 1 liter, has 3 significant figures, so your answer should have 3 significant figures. It's not difficult, but again, if you look at the table, it gives you how many calories per mole. You can work backwards, so you need to know how many moles. How do you know how many moles? Well, I need to know grams. How do I know grams? Well, I need to know the volume. So you can work backwards. This is one of those cases that's really not difficult. A little bit of practice, do several examples, and you'll breeze through this, I promise. And once again, if you want to separate it into separate steps, change the liters to milliliters. And when you get a number, change the milliliters to grams, and then change the grams to moles. You can do that, okay? I just like this because I can go real quickly and say, yeah, all of the units have been cancelled out, and that was kilojoules. I know I did it right. So I do have a number of exercises that you can do if you want to practice before any exam, something like that. You know what to do. And make an appointment with Wyson. The link is in the video description. I will give you that worksheet, and we can practice, however long it takes before you can do all the problems right.